This is the second of two videos about the exponential probability distribution using integration. So last time we learned about the exponential distribution, and you can see its makeup there, and this all relates to the previous video. Make sure you've seen that. This example, in fact the video is essentially some worked examples to help illustrate some of the former points and draw out a couple of new subtleties. And here's an example. So we have t minutes, the time it takes a librarian to locate a book. It's exponentially distributed. It has a mean of 3 minutes. So we've got two things to find: the probability density function of t and the probability that it takes her less than 2 minutes to find a book. Bear in mind that this is at the easy end, and a lot of questions you'll just be finding part B straight up. Okay, so this one's a scaffolded one to get us started. Sometimes we go straight to that sort of thing, so you'd have to know to do that. So starting with part A there, so we know the mean is 3 minutes. Be careful of the units you're working into. Some tricky questions might use seconds somewhere and then minutes in other places and things like that, so be careful of those little tricks. So if the mean equals 3, the mean also equals 1 on lambda. Thus, we have lambda equals 1 on 3. That's important so we can build the function. So the function will be, and we're looking at cases where x is, well actually t, we're looking at t for our symbol there, so perhaps I should have put t in there. Anyway, we're looking at time t, so it's really f of t. T is greater than 0. So we have lambda e to the negative lambda t, where t is at least 0. And we have a value for lambda, it's a third, so our function f of t will be a third e to the negative t on 3. So there's part A done. So for part B, we're looking at the probability that it takes less than 2 minutes. So we write that probability statement down where capital T is less than 2. And that equals the integral from 0 to 2 of our function. Take the integral. Note the limits. Substitute. And we've got negative 2/3 there. And minus negative makes a plus. And we've got 0 there. That comes out to approximately 0.4866. Now, the example we just did links to what is described as the cumulative distribution function of an exponential random variable. So the word cumulative was demonstrated in that previous question because it's everything up to 2, not including 2, but because it's a continuous function, this and that are the one and the, whoops, that's a 2, whoops, less than or equal to 2 or less than 2 is the same. Okay, so there's no distinction there because it's a continuous function. What we have in general is the integral such that we have something cumulative denoted here is from 0 to x of our familiar function. Apologies there. T, that should be, the variable is t. x is the parameter of integration, t is our variable. Okay, so integrating, we have negative, same story, negative e to the negative lambda x minus negative or plus. We have basically got a substitution there of e to the 0. I could write that in, and sorry, getting ahead of myself, that's better. Now we apply the limits. I was combining two steps in one, that's a big no-no. And now we make the substitution. I was getting a little bit ahead of myself. So we've basically got e to the 0 here. Anything to the power 0 is 1. So we've basically got 1 minus e to the negative lambda x. So we can say the following: for an exponentially distributed random variable x with parameter lambda, the following, as you can see there, for values of x at least 0 is provided. So that is actually almost like a shortcut. Okay, it's a result, instead of using integration, it's a result that comes from integration. Just a handy thing to know. You can use that unless it stipulates that you must use integration. Okay, so just be careful. If in doubt, use the integration, but if you're fairly certain you don't have to, that's a result that you can quote and then use. And finally, we're going back to an example from the previous video. You can see the function distribution there, density functions given by f of x there, and x minutes that a shop assistant waits before the next customer arrives. Okay, so it's exponentially distributed. What we've got to do is find the cumulative function of x and then find the probability that the shop assistant waits between 5 and 10 minutes for a customer. And so we have lambda equal 0.2 identified from the function. We're using the rule from previously there for x greater than or equal to 0. Notice that's a capital F because it's the result of integration. So we have the probability of 5 is less than or equal to x, which is less than or equal to 10 from the question. That can be rearranged in a convenient way. If you think about your distributions, oh, that's on a bit of an angle. Okay, but between 5 and 10, what we have is everything less than or equal to 10. Minus everything that's less than 5. Which leaves us with that strip there. Very crude diagram. Now, not that it makes any difference to the calculation. Those more keen viewers might have noticed that's less than or equal to and that's less than. Alright, now the less than or equal to must be so because 10 minutes is the threshold and it's inclusive. Okay. We must also therefore include the 5 minutes on our threshold by the same thinking. That means we don't remove the equals to 5, we must remove the less than. It doesn't make any difference to the calculation because it's a continuous function. So we've basically got capital F of 10 minus capital F of 5. You see, it doesn't make any difference, and we sub those values in. We get a probability approximately equal to 0.2325.